So what we're going to do is we're going to do these examples in place of the ones in your textbook. I think they're more in line with what you'll see on your final exam. So these are going to be word problems that relate to sinusoidal functions. And sinusoidal functions have so many applications in our day-to-day lives because they model anything that's periodic, anything that repeats itself. So we saw the Ferris wheel. If you wanted to go on a Ferris wheel and you wanted to create an equation of where you would be, then you could do a sine or cosine graph for that. This question is about depth of water because when tides come in and come out, it's predictable. It's not like, oh, the tide came in and stayed in for 15 days and then went out and back in 30 seconds. No, it's predictable. It follows a pattern. If we look at sunrises and sunsets, they follow a pattern. Anything that follows a pattern over and over again. It's really important for engines. Pistons go up and down. If you want to know where something is at a specific point, you have to model it with a sine or cosine graph. So here we have a question. This is an easier type of question because the equation's already given to us. So this is sort of the basic kind of question where an equation is given to you. Can you graph that? So here, the depth of the water is given by this formula. And if we were to sketch the graph, again, we're going to think about DAB-C. We're going to start with our d value, which happens to be 13.7. Our amplitude, and even though there's a negative out there in front, when we write our amplitude is always a positive value. So if we're thinking about our A value, that's going to be our amplitude. And our B value, well, our B value helps us calculate our period because our period is 2 pi divided by our B value, 0.16 pi. If you type that into your calculator, you get 12.5. And in this one, we have no C value. There's no shift. Some things to notice in this equation that are a little bit different than what we've had before. Instead of y equals, do you see that I have function notation? D of t. So d of t as a function, this means that depth is a function of time. So in this side of the equation, I have a t instead of an x. But basically, that means the same thing. You can interchange your variables. Often you'll use variables that represent what you're talking about. So d makes sense for depth, and t makes sense for time. So now to sketch this graph, and before I draw my scale, I do a little look at my data. Can you see from your data that 13.7 is going to be your middle value? And then you're going to go up 4.5 and down 4.5. So when I draw this, this might be a bad idea because I don't need any of this space below. This would be a really bad idea for drawing my scale. So when I go into my axis, I might think, oh, I'm going to draw it right along here because I don't need any negatives, right? I don't even know what that would mean if the depth of water was negative 5 meters. Try imagining you're on a 10-meter platform and it tells you that the depth of water is negative 5 meters. What would that mean? That means you jump, and then 5 meters before you're supposed to hit the water, you hit concrete? I'm not sure. I'm pretty sure it would not be a good thing. I think at the Y, they have the depth thing where they change it. I'd like to see one day someone get in there and change it to negative 2 meters and see what people think. Anyways, no, it does not make sense to have a depth of water being negative. So what we're going to do is we're going to pick somewhere along here for our 13.7. That's going to be our sinusoidal axis. And then we need to go up 4.5 and down 4.5. Now, when trying to think about 4.5, once you make 13.7, your scale has to be not perfect, but somewhat accurate. Does that look like about 4.5 as a proportion of that 13.7? Should be maybe about a third. Yes. If you want to bring it down and do something like the little break, that would be fine. Okay. For this one, I'm trying to make it accurate, so I'm going to take that break out. So if I go down 4.5, that'll go down to 9.2, and up 4.5, that same distance will go up to 18.2. So I've done my D value, I've done my A. Now my B value is my period. Remember, for our period, we mark, again, I'm going to mark one place where my period is and divide this into 4 equal sections. Half of 12.5 is 6.25. Half of 6.25 is 3.125, and that'll make this 9.375. So in the DAB-C method, normally we draw it temporarily after the DAB and then apply our shift. Can you see that this one has no shift? So we don't even have to draw it temporarily because we can just finish drawing this. So we have to look at our equation and just decide, where does this start? It's a coast graph. It's a negative coast graph. A negative coast graph starts at our minimum. And it's going to go minimum, middle, maximum, middle, minimum. And so now we've drawn this and drawn a sketch of our graph. Now, for part B, it says a bulk carrier needs 14.5 meters of water. I'm going to put 14.5 on my scale, and I'm going to draw water here. So we can imagine the depth of the water being at 14.5. So a bulk carrier needs, which is a big boat, needs at least that much water in order to go into the dock safely. Question is, how many hours per cycle of these tides can this bulk carrier be safe? So I'm going to pull up my highlighter. We need the depth of the water to be 14.5 or more. Does it make sense that it's only going to be safe from here to here? So with that in mind, we need to figure out what time does this happen, what time does this happen, and then if we subtract those two times, we're going to be able to figure out how long it can dock safely. Now, the first way that we're going to solve this is we're going to graph this on our graphing calculator. So we're going to take out our calculator. We're going to make sure that it's in radians. And the first thing I want you to do is I want you to get this green graph so it looks exactly the same as our sketch on your screen. You can watch this later. So I'm going to go to y equals. I am going to type this in, so I have negative 4.5. Notice it's a negative, so make sure you use the negative sign and not the subtract sign. Cos 0.16 pi, and then our equation has a t. Your graphing calculator only has an x, so if you put x in, plus 13.7. I'm going to hit my mode button just to make sure that I'm in radians, and I am. Now, if I hit graph right now, it's going to use whatever window I had from before. And that window might be completely useless, as this one is, because you can't see any part of the graph, because technically you're only looking at a part of the window where there is no graph in it. So this is where drawing your sketch at the beginning is going to be super important, because you could be searching forever looking for your graph, not knowing something about your graph in your window. So I'm going to go to my window button, and I'm going to think about my original sketch here. In my original sketch, my x values, I'm basically looking from 0 to 12.5. If I wanted to go a little bit further to the left for my x values, maybe I'll go from -3 up to 15. So I see a little bit on each side. The thing under here, which says XSCL, that's your x scale. If you want to be really fancy and have these ticky marks exactly where we have them at 3.125, you can change that to 3.125. And it'll have ticky marks every 3.125, so it'll have the 6.25, the 9.375, and the 12.5. For my y-min, I don't need to go much into the negatives. It's kind of nice to go a little bit into the negatives, so I might go -2, just so that you can see your x-axis. Because if you start at 0 or if you start at a positive number, you won't see that x-axis at all. But I know that the highest I went to was 18.2, so I might go up a little bit more, maybe up to 20, to see that. I won't be able to put these ticky marks at 13.7 and 8.2 perfectly like that, but I might make my scale go by 5s just so that it's easier to count than by 1s. Now when I hit graph, I get a graph that matches up perfectly with the graph that I have. The other trick that I want to show you is, let's say you screwed up miserably and you realized you screwed up miserably right away. So for example, can you see that if I put accidentally 1500 here, that would be a screw up for my x-axis? And then when I hit graph, I realize, oh no. And what's happening? It's taking forever, and you're like, come on, hurry up, I know I made a mistake. And if you push the on button, it stops whatever it's doing. At least it's supposed to. There it is. It stops it so you don't have to wait till the end. That's a helpful little thing, because sometimes you're like frustrated that you made that mistake. So the on button cancels what it's doing. Now I can go back to my window and go, oh, why did I put 1500? Stupid. There we go. And now it matches better. So now that we've got our graph matching up with our green graph, we need to add our water. And our water was at 14.5. So we go back to y equals, and in y2, a straight line, a straight horizontal line, is an equation y equals something. So if I do y equals 14.5 and hit graph, now that 14.5 gets put straight in. So if we're able to use our graphing calculator to match our graph, it is very quick for us to solve where these intersect, because your graphing calculator has a bunch of things built in to help solve things. And they're all above your trace menu. It says calculate. So if you go second, trace, it lets you figure out a bunch of things. In this case, we want to find out where our red line and our blue line intersected. That's number 5, intersect. And what's going to happen, it's going to say, be on your first curve. Can you see that my little flashing thing is on the blue one? You can push enter. Then it says go to your second curve. It automatically flashes on the second one. Sometimes if you have 4 or 5 graphs and you want to find an intersect, you can toggle between which 2 curves you want. But we just have 2, so it's going to be fine. It'll always ask you to guess, and it will always find the one that's closest to the ones you found. So it found this one at 3.48. I'm going to label that in here, 3.48. It found that first one. So if I want to find the second one, I'll go second, calculate, number 5, intersect again. I'm going to have to move my cursor until I get closer to the second one. And now when I push enter 3 times, now that it's closer to the second one, it finds that one. And that one happens at 9.02. So how long can it be safe? Well, if we go 9.02 minus 3.48, it's going to be safe for 5.54 hours. Now, the neat thing about this is all of this now is computerized, but someone had to have known this ahead of time. Someone had to make these models, and then computers figure out these equations. And so if you're the boat driver, the captain of some big ship, cruise ship coming into port, and it happens to be a port that the tides are going in and out, you want to know this information. Because it's not very fun if you have, how big are those cruise ships? How many people can go on them? Like the big ones? Like thousands. Like, does anyone know how the biggest cruise ship, how many people can go on one of those? Is it like 10,000 people? I have no idea. Never been on a big boat. But you can imagine 10,000 people who've each spent thousands of dollars to be on this cruise ship, and you have to tell them, I'm sorry, we're on the bottom of the ocean right now because our calculations weren't very good. We'll just have to wait here 8 hours before we can go. They're not going to be very happy. So these calculations are important, and we use them. You don't get to see them necessarily because they get used behind the scenes. Now, what I'm going to show you, I showed you the graphing calculator first because this is a calculator question. And if you get a calculator question like this, using your graphing calculator is way faster than doing it algebraically. But once you get to university, you might be asked to solve something like this, something like part B, without a calculator. So I'm going to walk you through part of it without the calculator. I'm going to show you where the calculator would still be needed. But you might be asked, maybe not without your calculator, but you might be asked to solve it algebraically. So I'm going to show you how does that work to solve something like this algebraically. So we start by plugging in the 14.5 for our depth. You don't have to write this down. If you want to put it in later, it's going to be on the video. But I just want you to watch right now. Okay? So you want to solve for t. Because we want to find out when is the depth 14.5, we need to solve for t. T is inside of cos. How do we solve for equations with something inside of cos? So we have to sort of go through what are the processes we want to do. We're going to want to get cos by itself and then do cos inverse, find our reference angles and so on, and solve for this. So how do I get cos by itself? Can you see that I would subtract 13.7 on both sides? Then divide by negative 4.5. Now I've got cos by itself. And what's complicated in this question is we got 0.016 pi t inside of cos. That makes it a little bit more complicated. If this was just a question like this, cos theta equals 3/7 or something like that. It's not hard, right? You know how to do that. You get cos inverse, find your reference angle, and then cos is positive in quadrants 1 and quadrants 4, and you'd find your angles. But the problem is that we have a lot of stuff inside instead of just a theta. So what mathematicians do when things look complicated inside and they know how to solve something simpler, they just make it simpler. They say, let's make theta equal to that big ugly thing inside the brackets. So then that'll change this equation to just be cos theta equals this. And I know how to solve that. Okay? Cos is negative. What quadrants is it going to be in? Quadrants 2 and quadrants 3. You'd need to find your reference angle first and then solve it for quadrant 2 and quadrant 3. So that's what we're going to do now. We're going to do cos inverse of that positive value to find our reference angle. And since we're dealing in radians, our reference angle becomes 1.39. Then we'll be able to say in quadrant 2, it would be pi minus our reference angle. In quadrant 3, it would be pi plus our reference angle. So we were able to solve for theta. Theta's either 1.7 or theta's 4.5. And once you solve for theta, then you can substitute back Because remember, we made theta equal to 0.16 pi times t. Now you could substitute back, and then you have an equation where you want to solve for t, dividing by 0.16 pi, and it matches up with that 3.48 that we found a lot quicker, I think, with our graphing calculator than doing all of this algebra. Similarly, you can take your answer in quadrant 3 and solve that one, and you get your time is 9.02. So you get the exact same answer algebraically that we did with our graphing calculator. Advantages and disadvantages of both. Well, if you know how to make your graph on your graphing calculator and can set your window up, it's way faster, right? But you have to have an understanding of how your graphing calculator works and the window, and you have to still be able to sketch things by hand first so that you can create that window. Advantages of the algebra, well, that's what you're going to be needing to do in university, and you need your algebra skills, so it's not bad to practice questions like this with algebra as well, because you're going to be asked to show that work when you get to these kind of questions in university. So this type of question generally doesn't happen on your exam for grade 12 because they want you to either do something algebraically, not necessarily graphing calculator. So these kind of questions show up more on like an applied exam where it really makes sense to use your graphing calculator. But the ideas, once you're done your grade 12 course, they expect you to be able to do this once you get to university. Okay, let's go to example 2. A Ferris wheel with a radius of 15 meters. That's a pretty big Ferris wheel. Rotates once every 20 seconds. It's also a pretty fast Ferris wheel. I'm liking it. Passengers start on the bottom, which is 1 meter above the ground. Let's graph this function and find its equation. So what I'm going to do for graphing this is I'm going to draw a picture of my Ferris wheel off to the side here. Nice, beautiful, newly painted red chairs and everything. Those ones are a little close together. That's okay. So there's my Ferris wheel, and right beside that, I'm going to draw my graph. So I've got my ground level here. This on my graph is going to be my height, and along here is going to be my time. So this one, unlike the first one where they gave us an equation, this one they're just giving us some information. And where are we at time 0? At 1 meter. So height is in meters, time is in seconds. So they tell us we get on 1 meter above the ground. What's the next point, or what's another point that I could put on my graph? Tell me a time and tell me where I'm going to be. You can put the sinusoidal axis. Sure, we can do that. Where's the middle going to be on this one? And how do we know that it's going to be at 16? Because the radius is 15, so if we go 1 up 15, then we'll get to the middle. Can you also write your maximum? Up another 15, we'll go up to 31 is the maximum that we're going to. Ooh, that doesn't match with my graph. Here we go. There's the maximum of my Ferris wheel there. Maybe that's the center just a little bit lower. Wow. Whew. Okay, good. So we've got 1 point on our graph so far. At 1 meter. Can you tell me another time and how high I'm going to be at that time? 5 seconds. And how did you know at 5 seconds that you would be at 16? Is that the first point that you thought of? Okay. How did you figure that out? It's right. At 5 seconds, we're going to be at 16. It's not. I'm curious because it's not the point that I would think of next. Okay. So we got this because our period is 20, right? So I probably would have put that 20 on there first and divided by 4. And then if you got this point next, I can understand that. Sometimes I put this point next at 20 because I know that in 20 seconds I'm going to be back to where I started from. But since we know things about sinusoidal graphs, once we've got our period and divided it by 4, half is 10, this will be 15, then it does this. If it starts at a minimum, it's going to go to the middle, then to a max, then back to a middle. And this is our Ferris wheel ride. So it said graph the function. We've done that. We need to find its equation. How many equations do you want to do? You want to do 4 again? Sine, cos, positive sine, positive cos, negative sine, negative cos? Or do you just want to do 2 of them? Or do you just want to do 1? Just sine? We'll do 1 in sine and 1 in cos. So if we look at this, can you tell me what your D, A, and B values are? We're going to leave the C value out because that changes depending on which graph you pick. What's our D value? 16. What's our A value? 15, because that's our amplitude. What's our B value going to be? 2 pi over our period, 2 pi over 20. Now you could reduce that to pi over 10, but you're going to find often in textbooks, they're going to leave the B value as 2 pi over a number, because if they leave it as 2 pi over a number, you can see that your period's 20 just right from the number, because whatever's on the bottom there will be your period. So now that we have that, we can write our equation. Our A value stays the same for sine or cos. Our B value stays the same, 2 pi over 20 for sine or cos. And our D value stays the same for our sine or cos graph. What's going